In this video, I want to explain how infiltration can be modeled with the green Ampt equation. I'm not really all that concerned that you understand all the details of the equation or even that you can use it to calculate infiltration. What I'm really after is that you develop a good understanding of the reasoning behind the equation and that you understand how and why it predicts that the infiltration rate is going to decrease with time, just like it's observed to do. So here we have a soil profile on the left and a graph of the moisture content of the soil on the right. Green Ampt is going to assume that the soil is initially pretty dry with a constant moisture content theta naught. This is almost certainly not entirely correct because we know that the hydrostatic distribution of moisture in the soil will resemble the soil moisture characteristic, but it's a good enough assumption for this model. Then we're going to assume that it rains so hard that we develop a puddle of water on the surface and that it continues to rain hard enough to maintain this puddle at a constant depth. In reality, the puddle will probably be only a few inches deep. With the upper surface now continuously saturated, water will begin to infiltrate into the soil like this. As it infiltrates, it creates a saturated zone or a wetted zone that grows in size with time. At the bottom of this wetted zone is the wetting front, where soil changes from unsaturated to saturated as infiltrated water fills up the pores. This is the really important part. The infiltration rate is the same as the downward movement of the wetting front, and the factor that limits how fast the wetting front can move down is the speed of water flowing through the wetted zone, which is saturated. The speed of water flowing through the saturated wetted zone can be modeled with the saturated version of Darcy's law, which is much simpler than having to use Richard's equation. So here's the equation we need. It's simply Darcy's law expressed in terms of the infiltration rate, I. It says that the infiltration rate depends on the saturated hydraulic conductivity. Remember, we're dealing with water flowing through the wetted zone times the hydraulic gradient. The hydraulic gradient is equal to the difference in head that drives the flow divided by the distance of flow. Since we're talking about water flowing through the wetted zone, the distance is L, and the head difference is the difference between the head at the top of the wetted zone at T and the head just below the bottom of the wetted zone in the unsaturated zone at B. One other thing to notice here, the hydraulic gradient is dimensionless. It's just a length divided by length, which means that the hydraulic conductivity has to have the same dimensions as the infiltration rate, or length over time. Hydraulic conductivity is usually described in terms of feet per day in the US or meters per day everywhere else. We're going to use the surface as datum. The head at the top of the wetted zone is actually the height of the puddle, but since this is usually really small, we often just assume that the head at the top is 0. The head at the bottom of the wetted zone is in the unsaturated zone, so we have to use the equation head equals elevation plus metric potential. The bottom of the wetted zone is located at a distance L beneath the datum, so its elevation is minus L. Putting all this together and doing some simple math, we can show that the hydraulic gradient that drives groundwater flow through the wetted zone is L plus H naught minus psi naught divided by L. Remember too that psi is always negative, so negative psi is actually a positive number. Every term in the parentheses here is actually positive. I think it's easiest to show how this works with an example. So let's try to calculate the infiltration rate with some simple assumptions. We'll assume that the puddle on the top is so shallow that its height is essentially 0. In other words, that the soil is completely saturated all the way to the surface, and it remains so due to rainfall, but there's no standing water on the surface. Like I said before, the depth of the puddle is usually small anyway, so assuming it's 0 doesn't really make any difference. We're also going to be clever and assume that the soil is initially at its field capacity, because we know that the metric potential at field capacity is -1 meter. This gives us everything we need to know to calculate the infiltration rate. So now let's calculate the infiltration rate just after the rain has started, when the wetted zone has only penetrated 10 centimeters or 0.1 meters downward. So L is 0.1 meters, and we can calculate delta H as 0.1 plus 0, that's the H naught, plus 1, that's minus psi, equals 1.1. And the hydraulic gradient then is 1.1 divided by 0.1, or 11. The infiltration rate is then simply 11 times Ks, the saturated hydraulic conductivity. I'm going to graph the results on the right with the y-axis representing the number of saturated hydraulic conductivities. So when the wetting front has reached 0.1 meters, the infiltration rate is 11 hydraulic conductivities. Now what happens when the front is penetrated a little deeper to half a meter, 0.5 meters? Delta H is 0.5 plus 1 equals 1.5 meters. And the gradient delta H over L is 1.5 divided by 0.5, or 3. And the infiltration rate has dropped to 3 times the hydraulic conductivity. Keep going. Now that the front is penetrated to 1 meter, delta H is 2 meters, and the hydraulic gradient is 2, and the infiltration rate has dropped further to 2 times the hydraulic conductivity. Finally, let's assume that the wetted front has penetrated all the way to 10 meters, over 30 feet down. Delta H is 11 meters, the hydraulic gradient becomes 11 divided by 10, or 1.1, and the infiltration rate is down to 1.1 times the hydraulic conductivity. In fact, maybe you can see that as L gets even larger, the hydraulic gradient is simply going to get closer and closer to 1. If I connect the dots on the graph, you can see that the infiltration rate decreases with L and asymptotically approaches a value of 1 times the saturated hydraulic conductivity, or simply the saturated hydraulic conductivity as L gets really large. This is the exact shape we expect for the infiltration curve, but notice we're plotting the infiltration rate versus L, not time. But these are related. When water is moving downward and the wetted zone is expanding, this is happening with time. L is increasing with time. With a little math, we can connect L with time, so the graph we obtained before describes actually exactly like what we'd expect the infiltration to do. Start out large and decrease with time, asymptotically approaching a constant value at long times. But now we can see what that long time value will be. It's the saturated hydraulic conductivity. So what do I want you to take away from this video? The green Ampt model describes ponded infiltration, infiltration caused by a continuous supply of water at the surface to fill a puddle. In this model, the infiltration rate is determined by saturated groundwater flow through the thickening wetted zone near the surface. It's the head gradient in the wetted zone that controls the infiltration rate. The head gradient is initially large, producing a rapid infiltration rate, but becomes 1 at long times, causing the infiltration rate to equal the saturated hydraulic conductivity.